This is so many thanks to the organizers for inviting me. I think this is a really good time for this topic. So I will be talking about tension between the Sitter uplift and the supergravity and 3D CFTs. I'm not a conformal field theorist, but my friends are. And this is why conformal field theories will appear twice in this talk, in two different situations. What I'll be talking about is based on a paper of last year about the Sitter CFT. It is based on a recent paper of May with Jacob Moritz, a paper to appear, which is also the title of this talk. And the underlying ideas and thoughts come from my review with Ulf Danielsson, which is about the Sitter Swampland conjecture. And I put conjecture in italic because it is a conjecture. It is not a proof. So we have been speculating in our review why this statement could be true, but we didn't put it as something that is certainly true. But the main arguments, I think, for why it's not unreasonable to believe that this could be true are outlined in this review. The interesting question is this the Sitter conspiracy, no de Sitter conspiracy or anti-de Sitter conspiracy? Does it work via this inequality? I think that's a very interesting question. And I just want to give my thoughts about what I saw the last couple of months on the archive. And then I go to the next part. So what is the evidence against the inequality? Obviously, all the Sitter vacua ever proposed in string theory. Right? That's an obvious statement. There was an interesting remark about the Higgs potential in the standard model. Then Joe Conlon wrote a recent paper explaining that for single killer Calabi-Yau's, you expect at least without SUSY breaking effects, you nonetheless expect away from the ADS minimum that there be the Sitter critical points which are unstable. And then of course people mentioned the classical de Sitter solutions immediately right after Qumrum's talk at strings. So is this evidence against? Well, of course, this is what I will try to criticize a bit in my talk, all these Sitter vacua. I don't think it is easy to debunk this argument of Hebecker et al. I don't know how to do it. I don't think one can. The point of Joe Conlon, could be true, but then you need to trust the ADS vacua he talks about. You might have reasons to worry about them. But I don't believe that at this point the classical de Sitter vacua should be considered counterexamples, because none of them are at weak coupling. So as long as they're not, I wouldn't call them counterexamples. What they have all 2, 3, and 4 have in common is that they are all tachyonic. So then I think it's very natural to wonder if the Sitter Swampland conjecture works via an inequality, should we not take into account second derivatives into the inequality, which has been suggested by some people already, okay? I just want one remark also about a very interesting paper by Tim Raze and Renata Kalos, which I liked a lot. And they said, well, all these tachyons you were fighting with when you were constructing classical de Sitter vacua, we have a possible way to remove them using anti-DC branes. I think it's a very beautiful idea. However, I am not entirely convinced it works. Tim will be talking about it, I think, so I just want to give you my 2 cents. So it is known that anti-DC branes can actually decay against H-flux via KK5 brane nucleation. And probe computations show that at least metastability is, of course, possible. But it's actually unclear even whether the probe computation is attainable in these classical de Sitter constructions. In fact, it's a bit worse. In a paper in 2016, we have actually shown that whenever you can put yourself in the supergravity regime, that anti-D6 branes behave quite different from anti-D3 branes, and a probe computation always fails. And I think that's an important difference with anti-D3s. They're actually behaving much worse. You remember the whole debate about anti-D3s, when you smeared them, it all got evil. Well, anti-D6 branes are very similar to smeared anti-D3 branes, okay? So I'm a bit worried about it. So I don't think it's unreasonable to expect that these backgrounds suffer from perturbative brane flux decay. But if not, I think it's very cute because this might be our first handle on maybe getting classical de Sitter solutions. They are not phenomenologically interesting, but they're interesting purely theoretically, okay? Because life is simpler when it's classical. But anyhow, the feeling I get when looking at classical de Sitter model building, it's more like, you know, trying to evade instabilities is like whacking a mole. This kind of game, you know, you try to solve the tachyon we always had by introducing a new ingredient, you kill it, and then another instability rises from another direction. That's the feeling you get when you work on this topic. And this is why I sometimes, you know, believe in this, or actually start thinking that the conspiracies against de Sitter, actually, there's something behind it. So, but let me talk about what most people of us look at, and this is the vanilla corner of the M-theory diagram. Most of string cosmology, but not all, has been focused on type 2b. And of course on, you know, corrections, you could call them corrections to Giddings-Kaczor-Polchinski. And I want to outline 4 problems with them, okay? So I call problem 1, is literally called, no, it's called problem 0, because it even has nothing to do with string theory per se. And that is the question whether the Bunch-Davies vacuum is physical. And I don't think we can ignore this question. And by trying to read a bit on this literature, I get amazed that those people, in my opinion, of all those people that actually think about this question, seriously, spend a lot of time on it. I think this community is almost split into half. Half of the people that work on it think Bunch-Davies is unphysical. The moment Bunch-Davies is unphysical, you get into troubles with de Sitter stability already at the point of view of quantum field theory. Okay. And the second problem is also before supersymmetry breaking, as pointed out by Savsetti, he thinks that actually starting with non-SUSY GKP and then restoring supersymmetry by adding non-perturbative quantum effects, he says it's a dangerous starting point because your starting point is actually a runaway, a classical runaway. This classical runaway, by the way, is only there when you start introducing alpha prime corrections to GKP. And then there's a whole debate on whether, you know, can I even think about adding instantons? What does it mean, right? I mean, some kind of a non-equilibrium quantum field theory where I don't have a vacuum. Nonetheless, I'm talking about instanton effects. I personally find this discussion too complicated, and I don't have an opinion. But what I do find interesting is what Ulf Danielsson pointed out. He says, actually, if you think about it deeply, these two, problem 1 and problem 0, they're actually closely related. And I think Danielsson will be talking about this tomorrow. What I know much more about is the 6D backcorrection of anti-branes, which is the uplift or the general uplift ingredient. Many people worked on it. I cannot summarize it. I hope there will be a review soon, but we have been saying it already for 4 years. But let me give you my biased interpretation of the research that went into this. And people here might disagree. They're welcome to say. So the main issue that first was the center of attention was at the moment I tried to actually understand what these anti-branes are and how they backreact. We found a non-physical singularity in the supergravity fields. And this non-physical singularity is very worrisome. It's not just a singularity. In fact, if you think about what it physically does, it gives you arbitrarily fast brane flux decay. So if this singularity would be there, I mean, of course, you need to cut off at string theory scale, etc. But still, you would say, okay, the system is unstable, it's side of the hill. And then there was a paper of Polchinski saying, well, and many collaborators saying, well, we don't think this is correct. We can probably not describe anti-branes in supergravity, but if you do proper string theory, and which was not done in that paper, it still uses effective field theory, they argue there is no problem at all. And this singularity is harmless. The thing I want to explain is that I'm not saying I'm disagreeing with this, but our point is that supergravity is smart enough. The moment I take my charges and my fluxes such that I have a classical background, I can talk about it, then we actually have shown if, you know, using some GR techniques that the singularity is most likely not there, or the reasons to believe in the presence of a singularity have disappeared. I have no time of explaining this, I just wanted to mention this, okay? But you could say, this whole thing was a red herring, but I'm not sure. And I think there were many follow-up papers in Saclay, written in Saclay, but also recently a paper in Japan, where I think this whole research just made people digging in the right hole. And then a lot of complications appear, such as brain-repelling tachyons and many other problems. So I don't think we entirely can settle the issue about anti-brain stability. But let me talk about another problem with anti-brains, which was discovered by Moritz, Ratolazza, and Westphal. And this I call 4D back reaction of anti-brains to distinguish it from the other thing. 4D back reaction in my language, or in their language, just means how 4D moduli reshuffle the moment I add the SUSY breaking source. Okay, that's 4D back reaction. Let me not do justice to this paper of the DAISY group by actually summarizing it in 2 equations. I will probably fail, but I want to give you the punchline of the paper, okay? So they say, well, there were arguments by other people that the gaugino condensate, it's a strongly coupled field theory effect. You cannot compute it in supergravity. What you can compute in supergravity is how it couples to the closed string mode. So how the gaugino condensate sources background fields and how it sources the metric. Okay? And by that, you just take a D7 brain action, you take the fermionic part, and you keep all the fermion bilinears. And then you basically end up with this term. And then we can actually understand how to do KKLT in 10 dimensions. We just say, okay, for some, the strong, the theory is confining. In the end, this value is non-zero. We don't know what it is, but we put it non-zero, and then we do the 10D calculation. Okay? What 10D calculation? They repeated the GKP type calculation, where you're shuffling, the Einstein equations. You do a lot of work, and then you end up with an equation like this. Okay? So what is this equation? This is not important. The point is that you need to integrate this equation over the internal manifold, right? Those of you that worked on GKP know this equation. So this is 0, right? All these 2 terms are positive, manifestly positive. In the original paper, so they computed this. This is new. Okay, that's what they've done. And then this whole thing is positive, right? And this is how KKLT works. Because then to get 0, this has to be negative, and that's the KKLT anti-de Sitter minimum. In a paper that will soon appear, we just want to point out there was some small computational error, which actually changes this result a bit. This is not quite positive definite anymore, but near the KKLT point, it has to be. Okay, so the only thing I want to say is there is still a lot of work to properly understand gaugino condensation from a 10-dimensional point of view. So what was then the issue raised by the people in DAISY? They said, well, now let's add an anti-brain. Let's add an anti-brain to this equation. And what happens, you just get an extra term here. And guess what? You probably know this extra term has just the same sign as all the other terms. So that is a bit strange, because that means no de Sitter, right? And you could say this doesn't make any sense, but actually you can make sense out of it from a 4D point of view. The thing, what this means, is that in fact, you can translate it into saying that the volume modulus has shifted, okay? That's a long story, but so I'm not going to motivate it, but the bottom line is this, okay? Just look at this picture. So this is a KKLT ADS minimum, and then you start adding anti-brains. There is no problem at all, at least in the computation. You don't see an error in getting non-supersymmetric ADS. But what happens is that each time by adding some SUSY breaking energy, you see the minimum of the volume modulus is shifting. It's shifting to the right. Okay, and then the effect is such that exactly when I want to lift to positive vacuum energies, that's when the system is run away. And I like this a lot because this is a beautiful illustration of the Swampland inequality. Okay, and I think this is what the 10D equations are telling us. So I said there was a small, computational error, but what we have been checking is that it doesn't affect the conclusions of the paper by the group in DAISY. And the main thing we can argue is that there is at least a loss of control of the effective field theory the moment I really want to lift to the Sitter, all right? So you can wonder, what is the way around problem, these 2 problems that I mentioned? Maybe the problem with unstable anti-brains, which is not entirely settled. So the problem with the 4 and the 6Z back reaction. Well, there's one way out, which was suggested in the paper by the DAISY group as well. They say, look at the following kind of ADS vacua. We're going to look at a special class. We're going to look at SUSY ADS vacua for which the vacuum energy can be tuned to 0 from below while keeping the masses of all modes fixed. Then any form of SUSY breaking will necessarily lead to the Sitter. And I agree with that completely. So what am I saying? In a picture, So say this is a standard landscape ADS solution. What we want is we want to squeeze this and at the same time start squeezing this. Okay, then you get arbitrarily close to Minkowski. Imagine just perturbing this system with any kind of SUSY breaking ingredient. Since the masses are very high, you're not going to jump out of your vacuum and you get the sitter. And now here is our claim. Oops, sorry. These vacua are in the swampland. Okay, so this I suggest as a new swampland constraint. There's a set of ADS vacua which we say cannot exist. And what is our evidence? Let me look at the first example. In the literature of such an ADS vacuum, the first I know is the racetrack fine-tuning of Kellogg's and Linde. So for those that forgot, the idea is that you have two stacks of 7 branes, so a direct product gauge group. And you're going to tune the ranks of these gauge groups to be almost the same, but much bigger than 1. Then the effective potential looks like this. So you see, well, here it's tuned to Minkowski, but say it's a very tiny negative CC, it's supersymmetric, and there's a very high mass, okay? So what did I show with Jakob Moritz in a paper of May? We say, okay, the moment you start looking at the axions in this theory, exactly when you do the fine-tuning, and only when you do that fine-tuning, something bizarre happens. The effective axion decay constant becomes parametrically large in Planck units. Again, the weak gravity conjecture is not proven, so you say, I don't care, fine. But to me, it's very interesting that exactly the thing that you want to get control de Sitter is talking to the weak gravity conjecture for axions. To me, that's a sign that we have to be really careful in believing the racetrack superpotential. But I have a better argument, okay? And this is where CFTs come to the fore for the first time, and that's using the conformal bootstrap. So let us consider the CFT dual to the supersymmetric racetrack ADS, if it would exist, okay? So this condition that I've given here, and let's do it for any kind of ADS space, which obeys this condition. So that the mass of the lightest modulus, think of the second derivative here, in ADS units, is much, much bigger than 1. So it means that I'm tuning this to 0 and I'm squeezing this, okay? That's what this inequality means. So I'm looking for this kind of ADS vacua, and all modes should obey that equation. That means it's it's very gapped, so to speak. This means from a dual CFT point of view, here is my equation, this is what I said that needs to happen. It means that all of the operator dimensions, all of them are super large. If you say that to any conformal field theories, you say, yeah, you have to show me an example of such a CFT because I haven't seen one. So then you can wonder, shouldn't the bootstrap maybe, show that this is impossible, right? And the bootstrap at least implies it's difficult, and there is actually a no-go that you cannot do it if the CFT is local, but that's good. That's what we have. We have an energy momentum tensor because there's a graviton. The CFT is unitary. We also have that. And the CFT is parity preserving. That is a constraint, okay? And if you do that, then this paper, 2017, not 15, shows that if you look at the T4 correlator, which is one of the general model-independent or theory-independent correlation functions you can look at, that they derive a beautiful bound saying there has to be a parity-preserving operator with dimension smaller than 7 and a parity-violating operator with a dimension smaller than 12. And that means that the moment, so that means it cannot be done. That's it. That's a CFT claim that it cannot be done. So then you can worry, okay, what about this condition of parity preservation? Of course, that is not a holy principle at all. I think the most easy way to translate it into gravitational language is actually to say that in your supersymmetric vacuum, the VEV of your axion is 0. And that doesn't need to be the case in the landscape vacua, but if you take the original example, for instance, of the racetrack model, then the VEV of the axion is 0, so the dual is a CFT preserving, parity preserving CFT. By talking to some bootstrappers, they say, well, it's not because, the moment I start violating parity that these bootstrap bounds will not hold. It's just that it's not computed yet. Okay? And they're doing this at the moment. I don't know when these results will be out because it's a lot of work. But they expect to find similar bounds in the general case, although they have no proof yet. So I think we have to wait. What I like about this is that the weak gravity conjecture, let's take the racetrack case where we investigated that we violate the weak gravity conjecture, is now beautifully consistent with a conformal bootstrap. Whereas this is a conjecture, this is very serious calculation. So that I like a lot. I think it's a very non-trivial connection, which is beautiful. So let me end by also talking about CFTs, but in a different context. You say, okay, imagine for a moment that this no de Sitter conjecture is correct. What about ds-CFT? I think we should care about ds-CFT because it's a possible way to define the Sitter space, non-perturbatively and so on. But as you know, ds-CFT is tough, and there are multiple reasons for them. First of all, the most trivial reason is that you cannot weak-rotate anti-de Sitter space in some string compactification to get de Sitter. That is very well known. And another reason, which is related, is that we don't know of a simple de Sitter background. And I was contemplating maybe not even, there doesn't even exist any kind of de Sitter background. Another reason is that the operators in general will be funny. They will have complex dimensions. Here is the equation for de Sitter. That is an extra minus sign. And that's already a bit bizarre. And in my opinion, the real reason, and I'm surprised why I don't read about it more, is that there are good arguments that if de Sitter exists in string theory, it certainly is at best metastable. But the way I understand holography, if your theory has a clock and at some point it's going to decay, I don't understand how you can have a CFT dual because the CFT doesn't have a time scale, all right? So that's why in string theory, there should not be a ds-CFT correspondence. Nonetheless, there is a counterexample. And I think it's very difficult to say that the counterexample is wrong. I think it works. And the counterexample is ADS higher spin Vasiliev theory, which is holographically dual to the O and to free vector models. And what has been shown by these people is that this correspondence can be weak rotated. It's the first time that an ADS-CFT correspondence can be consistently weak rotated to a de Sitter CFT correspondence. So I want to, think about this in the light of the Oguri-Waffa conjecture. For instance, what is said about non-SUSY ADS, we don't expect that a non-SUSY ADS, non-SUSY CFT duality cannot be. Although they say in their paper that the moment you apply it to higher spin, that doesn't need to work because I have an infinite amount of fields, etc. We also say that the Sitter cannot be SUSY. So for a similar reason, you could say ds-CFT cannot work. And of course, I agree with all these things. But you could actually still contemplate, why not supersymmetric? Why do we say supersymmetric ds cannot exist, right? And the usual reasons, well, actually, in fact, counterexamples exist, and it's called type 2a star and type 2b star string theories. But the thing is, they always have ghosts. So the problem is ghosts, okay? And that's consistent with classifications of the Sitter superalgebras. They tell you should always have ghosts, all right? But it was conjectured by Hull and then later by these people that maybe these ghosts can make sense in some unconventional way. And this is what got us interested. So what we have shown, well, what we have evidence for, we haven't shown it, is that in fact we can supersymmetrize the higher spin de Sitter CFT correspondence of Anoninos et al. And this work, supersymmetrizing Vasiliev theory, is hardcore. We haven't done that. This was done by Sundel and Sesgin. What we have done is the easy bit, just supersymmetrizing the SPN free field theory. There was not so much work. And what we have given evidence for is, well, everything works. I mean, whatever you compute, these things naturally match. So the duality is there. And then you wonder, are there any ghosts? But talking about ghosts in higher spin theory is very non-trivial. What do you mean with a ghost? There's not an obvious Lagrangian or something. So the best thing you do is you think about what is the definition of ds-CFT. Malacena told us what we're computing in ds-CFT is the Hartle-Hawking wave function. So what would be a ghost? A ghost would be the moment that, the point of the Hartle-Hawking wave function is when I square it, I get a probability. The signal of a ghost would be that the probability is not peaked around a vacuum, okay? So what did we compute? We were looking in all possible directions, and we always find, and this is non-trivial, if you do these calculations, it can easily go wrong. We always find that our probability peaks. And what is this? So this is a deformation away from the vacuum, one of the things that are your arguments in your partition function, okay? So this to us is an evidence that it could very well be. So how can this be? If you look at the original paper of Hull, he already speculated that, well, maybe these ghosts, these supergravities with ghosts, the moment I put in all my higher spin fields of string theory, somehow they remove these ghosts, okay? But what I like about our example is the moment you do higher spin theory, you're sort of taking the tensionless limit of the string, and that means that you integrate in, you're forced to integrate in all of the massive string modes. So our calculation has that taken into account, and we surprisingly don't see any ghosts. So I think Hall's intuition might have been correct. So let me conclude. The main thing, my main message is not so much about higher spin theory, actually not at all. The thing I want to say is this, that the de Sitter landscape in string theory, if there, I think has huge implications because it potentially explains the CC problem, let's not forget that. So it better, if something is huge, we need strong evidence, okay? And I don't think, so ideas like KKLT are smart, they can potentially be correct, but let's not call it strong evidence so far, okay? Likewise, we do not have strong evidence for the no de Sitter conjecture, okay? So the only thing that is needed is more work. And what I like a lot is that the current paradigm shift is exactly what we needed, because we will do more work either on this side or on this side. And it is needed because it's so important, you know, what we're trying to do. But I cannot end by giving you my opinion. If I would have to bet now, this is how I think what the situation will be. And I hope we know in, say, 10 or 20 years from now. Thank you.
Questions for Thomas?
So the connection that you mentioned between Swampland conjectures and the bootstrap is very interesting. I thought that for any effective field theory that you write down in the bulk, Witten diagrams basically satisfy crossing symmetry, so they are a solution to the bootstrap, ordered by ordering 1 over n. So how do you reconcile these two things?
Well, it means that it's not a string background.
That it's not a string background?
Yeah. I mean, if you say you use Witten diagrams, then, well, it just means that I don't have a holographic dictionary, right? Then I get a contradiction, so there's no holography, but that's what I'm saying, there's no background. It's not a consistent background. I mean, I'm just saying, Miguel, I can write down for you, and I think you would agree, I can give you any classical Lagrangian. Here is Lagrangian. I'm declaring it to be UV completable. And then, of course, I can trivially write down Lagrangians that violate bootstrap bounds. I mean, that everybody can. I'm just saying the racetrack Lagrangian is an example.
Right. No, but my point is that when you write down a bulk Lagrangian, normally it satisfies any effective field theory you write down satisfies the bootstrap bounds, ordered by ordering 1 over n.
But I'm talking... Well, that contradicts what I just said, right?
Yeah.
So I'm a bit confused, yeah.
Yeah, okay.
We should talk about
it. So I think it's extremely interesting that you have this relation between, or this way to exclude what I would call a gapped ADS vacuum, right? Using CFTs. But I have a following suggestion. You could consider, for phonological purposes, a metastable, very long-lived gapped ADS, right? So it could be ADS, but nevertheless metastable, decaying to something much deeper. Then you can't use CFT arguments against it, as far as I understand, but you can nevertheless uplift it, producing potentially long-lived metastable de Sitter. So there is kind of a loophole here, which for those of us who still hope for the de Sitter landscape, right?
You're entirely correct. That's also the problem of trying to understand large volume scenario. I think with a CFT dual, it's difficult to know whether we can have a CFT dual. But it's a bit strange that all of the standard arguments for the Sitter, which we then use in, say, in a supersymmetric context, and suddenly we get a problem, then we say, but then it's non-supersymmetric. I would say by then, okay, there's something clearly going on. And, you know, that's me. But you have a point, certainly.
So you didn't mention de Sitter supergravity. Is there a reason?
Is there a reason?
So
for me, this whole development on the Sitter supergravity is interesting, but I have never understood the connection with all of this. Never. So this Sitter supergravity is the moment you say, okay, I trust these Sitter solutions, then there must, because I break supersymmetry, there is always a nilpotent superfield description with a given cutoff. And I agree with that. And it's interesting to find those descriptions, but they, to me, have no relation with trying to establish the consistency of the sitter in string theory.
So in the examples that Hall studied and the ones we studied, it wasn't unitary. So we had so it wasn't the unitary duality. So that means the gravity side is also not unitary. So presumably that's not what we want. But that's I think a big caveat. Also, I think the same thing was true with Strominger et al. They also violated spin statistics. They didn't have unitary system.
But their gravity theory is.
Their spin system was they had the things with wrong spin statistics. So.
No, but that is true. So the CFT is a Euclidean CFT that violates spin statistics, but their argument is still that the bulk theory should be
there's no problem with getting a duality, which looks more or less normal, but the statement is that it cannot be unitary. But
you're talking whether the bulk theory is unitary?
If the boundary and bulk are equivalent, which they are, that's what holography means.
So when
if one is bad, both are bad, in other words.
Maybe, Strominger is your colleague, maybe should ask, but when I talk to some of them, they say the point is that actually the bulk will be actually unitary.
No, that
because time is somehow emergent, and it's the combination that is unitary. Because
if one piece is bad, the whole thing is bad. So
okay. That's not how I understand it, but okay. Yeah.
I already discussed with you, but maybe it's worthwhile, maybe Fernando can comment. In the context of the bound, so the KKLT would have a dual CFT with a dimension which was bigger than typically 100, you said, or 1,000? The first view, but there's no tower of this state. The KK modes are bigger than 1,000. Yes. Smaller. The dimensions in KKLT are smaller than one?
The thing that I have in my mind is the large volume, and I think they're all suppressed by one or the volume. I guess KKLT is similar, but I'm not sure.
I thought that the scales are such that the thing is much bigger than the internal manifold. You're not saying that's the case?
No.
Similar to the bounds that he was talking about?
I'll double check, but I
Thank Thomas again.